In the unending silence of the void, where distances are measured in light years and time is counted in eons, humanity has always cast its gaze upward, asking the two most profound questions that can be conceived. Where did all of this come from? And from that vast cosmic tapestry, where did we come from? For generations, our answers were confined to mythology, to philosophy, and then to the glimmers of light captured by our telescopes. We built greater and greater eyes, each one peeling back another layer of the cosmic onion, each revealing a universe more ancient and more magnificent than the last. We thought we were closing in on the story of our genesis. We had a timeline, a sequence of events, a grand narrative of cosmic evolution. It was a story of patience. A universe born in fire, cooling in darkness, and then, slowly, painstakingly, over hundreds of millions of years, igniting its first stars, and then gradually assembling its first fledgling galaxies. It was a story that made sense. It was orderly, but it may have been entirely wrong. Out beyond the orbit of the Moon, a million miles from Earth, drifts a creation of pure genius, an instrument of impossible precision. Its gaze is fixed not on the familiar stars of our night, but on the darkness between them. It is a time machine, its segmented golden eye collecting photons that have been traveling since the dawn of the universe itself. This is the James Webb Space Telescope, and in the silent flood of data it sends back to Earth, it is not just confirming our story of creation, it is tearing the pages out of the book and forcing us to start anew. The images it has captured, from the very edge of observable reality, show us something that shouldn't exist, something that defies the laws of cosmic growth as we have written them. Did this revolutionary observatory just stumble upon the true origin of our cosmic home, and in doing so, has it forever altered the story of us? To comprehend the revolution that is now unfolding, we must first understand the journey that brought us here. Our quest to see the beginning of time is a story of light. For centuries, we were explorers confined to a single, narrow shoreline of the electromagnetic ocean, the sliver of visible light our eyes evolved to perceive. Galileo's first spyglass revealed the moons of Jupiter, shattering the celestial spheres of antiquity. Larger and more sophisticated instruments followed, painting a portrait of a universe filled with immense, swirling islands of stars we named galaxies. Then came the Hubble Space Telescope, a triumph of human ambition launched above the blurring distortion of Earth's atmosphere. Hubble showed us galactic collisions, the birth of stars in stellar nurseries, and the faint, ghostly smudges of galaxies billions of light-years away. It took us deep into cosmic history, producing images that transcended science and became cultural icons of our place in the cosmos. But Hubble, for all its power, had a fundamental limitation. It was, for the most part, an eye that saw as we do, in visible and ultraviolet light, and when you are trying to see the very first objects in the universe, that type of vision is like trying to see through a dense, impenetrable fog. The universe is expanding. This is the foundational discovery of modern cosmology. Every galaxy is rushing away from every other galaxy, a concept that rewinds to a single, infinitely dense point in the past, the Big Bang. This expansion has a profound consequence for the light that travels through it. Imagine a beam of light as a perfectly rhythmic wave. As this wave journeys across billions of years of stretching space-time, the wave itself is pulled, elongated, its frequency lowered. Light that began its existence as brilliant, high-energy blue or even ultraviolet light is stretched down the spectrum, through the yellows and oranges, and finally into the long, cool wavelengths of infrared. This phenomenon is called cosmological redshift. The farther away an object is, the faster it recedes, and the more its light is redshifted. The very first stars and galaxies, burning at the dawn of time, sent forth a torrent of brilliant, visible light. But after traveling for over 13.5 billion years to reach us, that primordial radiance has been stretched into invisibility. It has become a faint, thermal glow, a whisper in the infrared. Hubble could not perceive it. To see the cosmic dawn, we needed a different kind of eye. We needed a machine that could capture this ancient, spectral ghost. Building such an observatory was one of the greatest technological challenges humanity has ever undertaken. The James Webb Space Telescope is not merely a successor to Hubble. It is a different species of instrument altogether. Its primary mirror is a breathtaking mosaic of 18 hexagonal segments of beryllium, each coated in a microscopically thin layer of pure gold, an element chosen specifically for its supreme ability to reflect infrared light. When unfolded in space, this mirror spans over 6.5 meters, a giant, light-collecting bucket designed to catch the faintest, oldest photons in existence. The precision required is difficult to articulate. Each of the 18 segments must be aligned to within a fraction of the width of a human hair, working in perfect concert to form a single, flawless parabolic surface. This is a level of accuracy akin to scaling the entire mirror up to the size of a continent, and having no imperfection larger than a few inches. But even this magnificent mirror would be useless without another, equally audacious feat of engineering. Infrared is heat. The telescope itself, if warm, would glow with its own infrared light, blinding its sensitive instruments and drowning out the faint signals from the edge of time. To see the cold universe, the telescope must be colder still. It must operate at a temperature of just a few tens of degrees above absolute zero, that theoretical point where all atomic motion ceases. To achieve this, JWST is shielded by a colossal 5-layered sunshield. The size of a tennis court, this structure of gossamer-thin, reflective kapton acts as a giant parasol, constantly positioned between the telescope and the sun, earth, and moon. Each successive layer is cooler than the one before it, reflecting and radiating heat into space until the observatory on the dark side is plunged into a profound, cryogenic cold. This is the machine we sent to hunt for our origins. A golden eye, chilled to the verge of absolute zero, designed to capture the last echoes of the universe's first morning. And when that eye finally opened, what it saw sent shockwaves through the world of astronomy. The established narrative of the early universe was one of slow, majestic assembly. Following the Big Bang, the cosmos was a roiling, opaque soup of elementary particles. For nearly 400,000 years, it was too hot for atoms to form. Light was trapped, scattering endlessly off free electrons. Then came a moment of transition known as recombination. The universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. Suddenly, light was free to travel. This is the origin of the cosmic microwave background, the afterglow of creation itself. But this release of light also plunged the universe into a period known as the Cosmic Dark Ages. There were no stars, there were no galaxies. There was only the primordial hydrogen and helium gas, drifting in near total blackness, governed only by the gentle, persistent pull of gravity. Our models, built on decades of observation and theory, painted a clear picture of what happened next. In the densest regions of this cosmic gas, gravity began to win. Clumps formed, slowly pulling in more and more material. After perhaps 100 or 200 million years of this gradual accumulation, the core of the largest clumps would become dense and hot enough to ignite nuclear fusion. These were the first stars, the so-called population 3 stars. They were unlike anything that exists today. Forged from pure hydrogen and helium, they were gargantuan, hundreds of times the mass of our sun, burning with an almost unimaginable ferocity. They lived fast and died young, exploding as supernovae after only a few million years. But in their explosive deaths, they performed a vital act of creation. For the first time, they forged heavier elements, carbon, oxygen, silicon, iron, and seeded the surrounding gas clouds with them. From these enriched clouds, the next generation of stars would form, and these stars, grouped together in small clusters, would represent the seeds of the first galaxies. The prevailing theory was a bottom-up model of cosmic construction. Small irregular dwarf galaxies would form first. Over hundreds of millions, even billions of years, these smaller structures would collide and merge. gradually building up into larger, more organized, spiral and elliptical galaxies, like our own Milky Way. It was a story of cosmic patience, of construction happening one brick at a time. This is what astronomers expected to see when JWST peered into the abyss. They anticipated finding faint, messy, barely formed proto-galaxies, the humble beginnings of the grand structures we see today. The first JWST deep field images were released to a waiting world. They were jewels scattered on black velvet, a window deeper into space and time than ever before. Every smudge of light in the image was a galaxy. But as scientists began to analyze the faintest, reddest, and therefore oldest objects, a profound sense of confusion and then astonishment began to spread. The infant galaxies were not what they were supposed to be. They were not small, clumpy, and chaotic. Among the oldest candidates, objects whose light had traveled for over 13.4 billion years, dating back to just 300 to 400 million years after the Big Bang, were galaxies that were shockingly massive. Some appeared to have stellar populations rivaling that of the modern Milky Way. They were also surprisingly well structured. Some even showed evidence of spiral arms or galactic disks, features that were thought to take billions of years of cosmic evolution to develop. The discovery was analogous to an archaeologist excavating a site from the early Stone Age, expecting to find primitive hand axes and crude shelters, but instead unearthing the foundations of a skyscraper. It simply didn't fit the timeline. The universe, it seemed, was in a hurry. It had gone from darkness to sprawling, mature cities of stars, in a fraction of the time our best models had allocated. These objects were nicknamed universe breakers because their very existence threatened to shatter our understanding of cosmic formation. How could the universe build something so big, so quickly? The slow, steady, bottom-up model of gradual mergers couldn't account for this accelerated timeline. It would be like trying to build a modern metropolis in a single decade using only hand tools. There simply wasn't enough time, and the available resources, the primordial gas, couldn't be gathered and converted into stars that rapidly through gravity alone. A new ingredient was needed, a new mechanism for super-fast construction. Scientists scrambled to find an explanation. Perhaps these objects weren't as far away as they seemed. Maybe their extreme redness was caused by something else, like immense amounts of interstellar dust. But as JWST's powerful spectrographs went to work, dissecting the light from these enigmatic galaxies, the data was confirmed. Their redshifts were enormous. They were indeed relics from the cosmic dawn. The problem was real. Our story of origins was missing a critical chapter. And the most compelling, most audacious explanation points to the most mysterious objects in the cosmos. Supermassive black holes. Every large galaxy, including our own, has a supermassive black hole at its center. Sagittarius A*, the black hole at the heart of the Milky Way, is more than 4 million times the mass of our Sun. For decades, the assumption was that galaxies and their central black holes grew up together in a process of coevolution. As a galaxy pulled in more gas and merged with other galaxies, it would feed its central black hole, which would grow in lockstep with its host. The galaxy came first, and the black hole was a consequence of its growth. But the impossible early galaxies discovered by JWST have turned this idea on its head. What if the black hole came first? A radical new theory is gaining traction, one that posits the existence of direct collapse black holes. Imagine, in the very early universe, a colossal cloud of pristine hydrogen gas, so massive that it doesn't fragment into myriad stars. Instead, under its own immense gravity, the entire cloud collapses catastrophically, bypassing the star formation phase entirely and falling in on itself to form a black hole tens of thousands, or even hundreds of thousands, of times the mass of the Sun. These would be primordial black hole seeds sown into the fabric of the cosmos. Within the first couple 100 million years, these seeds would be game changers. They would act as potent gravitational anchors, overwhelming the normal, patient process of galaxy formation. Instead of gas clouds slowly coalescing, these massive black holes would create immense gravitational wells, voraciously pulling in gas from vast surrounding regions. They wouldn't just be feeding themselves, they would be creating a hyper-dense environment that would trigger furious explosive bursts of star formation all around them. This wasn't the slow brick-by-brick construction of the old model. This was like setting up a massive, prefabricated gravitational scaffold and having the entire galactic city spring into existence around it almost instantaneously. The black hole wasn't a feature of the galaxy, it was the creative engine. This black hole-first or top-down model could potentially explain the shocking size and maturity of JWST's ancient discoveries. It suggests the universe was born with the seeds of its own grand structures already in place. This fundamental rewriting of galactic history has profound implications for our own origins. It directly impacts the timeline for the creation of the elements essential for life. The Big Bang produced only hydrogen, helium, and trace amounts of lithium. Every other element on the periodic table, the carbon that forms the backbone of our DNA, the oxygen we breathe, the iron in our blood, the silicon in the rocks beneath our feet, was forged in the hearts of stars and scattered throughout the cosmos when they died. We are, as the famous saying goes, made of star stuff. In the old, patient model of galaxy formation, this process of chemical enrichment was also slow. It would take many generations of stars, living and dying over billions of years, to build up a sufficient concentration of these heavier elements, which astronomers call metals. Planets like Earth, which are rocky and rich in metals, could not have formed until the universe was sufficiently seeded. Life, as we know it, which depends on a complex carbon-based chemistry, would have to wait even longer. This placed our own existence relatively late in the cosmic story. But if JWST is correct, if massive galaxies were forming and churning out stars at a furious pace, just a few 100 million years after the Big Bang, then the entire timeline of chemical enrichment is drastically accelerated. These supergalaxies would have been cosmic forges, operating at maximum capacity. Their massive, short-lived stars would have rapidly synthesized vast quantities of heavy elements, and then expelled them in spectacular supernova explosions. The universe may have become metal-rich far earlier than we ever thought possible. The raw ingredients for rocky planets, and perhaps for life itself, may have been widely available when the universe was less than a tenth of its current age. This realization is a profound shift in perspective. JWST isn't just showing us the origin of galaxies, it is showing us the origin of the atoms that make up our world and our bodies. When we look at the light from an object like glass, Z1-3, one of these impossibly early galaxies, we are not just observing a distant astronomical curiosity. We are potentially witnessing the crucible where the very first life-giving elements were synthesized. On a galactic scale, the light from that galaxy began its journey long before our Sun or Earth even existed. It traveled across a constantly expanding void for 13.5 billion years, destined to be collected by a golden mirror and focused onto a detector built by beings whose own atomic ancestors were forged in similar cosmic cauldrons. The Discovery telescopes the vastness of cosmic time, connecting the biochemistry of our own planet directly to the violent, creative frenzy of the universe's earliest youth. This new cosmic narrative forces us to reconsider the timeline for life in the universe. If the ingredients for rocky planets and complex chemistry were present billions of years earlier than we assumed, it dramatically widens the window of opportunity for life to emerge elsewhere. The Copernican principle suggests that Earth is not in a privileged position in the cosmos. If life happened here, it could happen elsewhere under similar conditions. We have always wondered if we were the first. JWST's findings hint that we may, in fact, be relative latecomers to the cosmic stage. It is conceivable that life-bearing planets could have formed around stars in those ancient galaxies, billions of years before our own solar system coalesced from its cloud of gas and dust. It opens up the speculative, but now scientifically grounded, possibility of ancient civilizations that may have risen and fallen before the light from their home galaxies even began its journey toward us. Of course, With every great discovery comes a new set of even deeper questions. If massive black hole seeds are the answer, where did they come from? Does their formation require a new understanding of physics in the extreme environment of the early universe? Or could they be evidence for something even more exotic, like primordial black holes, formed not from collapsing gas, but from density fluctuations in the first seconds after the Big Bang itself? Furthermore, these discoveries are putting immense pressure on our understanding of the universe's invisible components. Dark matter is the mysterious substance that provides the extra gravitational glue, holding galaxies together. Our models of how dark matter should clump together in the early universe helped inform the slow growth model of galaxy formation. The existence of these massive early galaxies might mean our theories about the nature of dark matter itself are incomplete or in need of revision. JWST is just beginning its mission. What we have seen are the first postcards from the edge of time. Each new observation, each new spectrum analyzed, will add another piece to this revolutionary puzzle. Scientists around the world are now engaged in a feverish campaign to confirm the masses and compositions of these ancient systems, to hunt for even older and more distant objects, and to refine their computer simulations to see if they can recreate a universe that builds itself so quickly. The telescope has thrown down a gauntlet to the scientific community, challenging them to abandon old certainties and embrace a cosmos that is proving to be far more dynamic and creative in its infancy than we ever dared to imagine. We stand at a pivotal moment in human history. For millennia, our origin story was rooted in the soil beneath our feet and the myths we told around the fire. Then, science took us on a journey outward, from our planet to our star, from our star to our galaxy, and from our galaxy across the expanding universe, back toward the moment of creation. We built a narrative that seemed to fit the evidence we had. Now, an instrument of our own making, a marvel of glass and gold and cryogenic genius, has looked into the deepest recesses of the past and brought back a new truth. It tells us that the story of structure, the story of chemistry, the story of the potential for life, the story of us began almost as soon as the universe itself was born. We are the descendants of this unexpectedly rapid creation. The atoms within us carry the memory of those first furious stars in those first impossible galaxies. The light that traveled across the immensity of space and time to tell us this story is not foreign. It is the light of our own ancestral home. The James Webb Space Telescope has not given us the final, complete answer to our cosmic origins. Instead, it has done something far more valuable. It has shown us that the universe is more surprising, more mysterious, and more magnificent than we knew. It has shattered our old map and invited us to explore a new, uncharted territory. The cosmic dawn was not a gentle sunrise. It was a brilliant, explosive, and astonishingly rapid conflagration. And in its ancient light, we are, for the first time, beginning to see our own true beginning. What if the history of the universe has a secret chapter? A story of creation so violent, so utterly alien to our understanding of the cosmos, that it has remained hidden in the deepest shadows of time, waiting for a technology powerful enough to glimpse its ghost. We believe we know the story of stars. We believe we understand the inexorable patient growth of the gravitational titans that anchor our galaxies. But what if the first monsters to prowl the cosmic dark were not born in the ways we expect? What if they were something else entirely? Something that defies the very definition of a star. The evidence for this lost chapter is not written in stone but in light that has travelled for over 13 billion years to reach us, carrying with it a profound and disturbing paradox. It is a message from the cosmic dawn, and it tells us that our story of the universe might be completely wrong. When you look out into the night, you're not seeing the universe as it is, but as it was. The light from the moon is a second old, the light from the sun 8 minutes, The faint glimmer of our nearest stellar neighbour, Proxima Centauri, is a message from 4 years in the past. But with our most powerful instruments, we're capable of an almost unimaginable act of temporal voyaging. The James Webb Space Telescope is not merely a telescope. It is a time machine engineered to capture the faintest, most ancient whispers of a universe in its infancy. It gathers photons that began their journey when the cosmos was a mere fraction of its current age, when the very first structures were just beginning to crystallize from a uniform fog of primordial hydrogen and helium. Peering into these depths is like an archaeologist uncovering the foundations of a forgotten civilization. We expect to find the building blocks, the primitive precursors to the grand celestial architecture we see around us today. We expect simplicity. We expect a universe learning its own rules. In our local mature universe, these rules seem clear, even elegant. Stars are born from collapsing clouds of gas igniting into brilliant spheres of thermonuclear fire. They live for millions or billions of years, forging heavier elements in their cores, and then they die. The most massive among them end their lives in spectacular supernova explosions, leaving behind remnants either a hyperdense neutron star, or if the progenitor was massive enough, a black hole. These stellar mass black holes are the seeds. They are the modest ancestors of the galactic titans to come. Through a slow, methodical process spanning eons, they grow. They can merge with other black holes in cataclysmic collisions that send gravitational ripples shuddering through the fabric of space-time itself. More importantly, they feed. They draw in surrounding gas and dust, pulling it into a swirling, superheated accretion disk, a celestial maelstrom where matter is torn apart and heated to millions of degrees before taking its final plunge across the event horizon. This process of feeding, however, is not one of unrestrained gluttony. There is a fundamental cosmic speed limit on how fast a black hole can grow, a principle known as the Eddington limit. As matter falls inward, the intense friction and gravitational energy release a furious blaze of radiation. This outward-pushing torrent of light and energy acts as a counterbalance, a form of cosmic regulation that literally pushes away the black hole's next meal. It's like trying to fill a bucket with a fire hose that is so powerful it keeps blowing the water back out. A black hole can only consume so much so fast before its own dinner party becomes so bright and energetic that it drives away the remaining guests. This limit is one of the pillars of our understanding of galactic evolution. It dictates a patient, stately pace of growth. A stellar mass black hole, perhaps 30 times the mass of our Sun, would require not millions but billions of years of steady feeding and mergers to swell into the kind of supermassive black hole we see in the centres of galaxies like our own Milky Way, a gravitational anchor weighing in at 4 million solar masses. This is our model. It is tested, it is logical, and it fits the evidence of the universe around us. And then our time machine showed us the dawn. It pulled back the veil on an era just a few 100 million years after the Big Bang, a period so early, it should be the universe's nursery filled with cosmic toddlers. And in that nursery we found giants. Not just large black holes, but fully formed, mature, supermassive black holes, 1 billion times the mass of our Sun, already in place, already dominating their nascent galaxies. This is the paradox that has thrown astrophysics into a state of profound crisis. It is a discovery as shocking as finding a fully grown redwood tree that is only 3 weeks old. It simply should not be possible. The time between the Big Bang and the moment we observe these behemoths is a cosmic blink of an eye. There was not enough time for a star to be born to die to form a black hole, and for that black hole seed to grow to such a monstrous scale. Not even close. The Eddington limit, that fundamental rule of cosmic growth, stands as an unbreachable barrier. Even if a seed black hole had a perfect, uninterrupted buffet of cosmic gas from the moment it formed, it could not have physically accreted matter fast enough to reach the prodigious sizes we now observe. It is a cosmic crime scene. The evidence is right there in front of us, the colossal gravitational monsters, but the suspect, the slow and steady process of accretion and merger, has an ironclad alibi. It was simply not fast enough to have committed the act. So astronomers were forced to search for another culprit, another way to build a monster in a hurry. Perhaps they theorized the universe had a secret shortcut. This led to the idea of direct collapse black holes. In this scenario, you skip the star phase entirely. Instead of a cloud of gas forming a star that later collapses, what if a truly immense pristine cloud of primordial gas, Hundreds of thousands of solar masses could collapse under its own gravity all at once directly into a single intermediate mass black hole. This would give the universe a tremendous head start. Instead of starting with a seed of 30 solar masses, you would start with one of 100,000. Suddenly the timeline to reaching 1 billion solar masses becomes far more plausible. This direct collapse model is an elegant and compelling idea, but it comes with its own severe, perhaps fatal set of problems. The conditions required for such an event are exquisitely precise, almost impossibly so. For a gas cloud to collapse directly without fragmenting into countless smaller stars, it must be exceptionally pure, composed of almost nothing but hydrogen and helium, the raw elements forged in the Big Bang. The presence of even trace amounts of heavier elements, the metals created inside later stars, would act as a powerful coolant, allowing the cloud to fragment and form a star cluster instead of a single monolithic object. Furthermore, this pristine cloud must be bathed in a very specific intensity of ultraviolet radiation from nearby newly formed galaxies. This radiation has to be strong enough to destroy any molecular hydrogen, but would also help the cloud cool and fragment, but not so strong that it blows the gas away entirely. It is a cosmic Goldilocks problem of the highest order. The environment must be just right. While not impossible, these conditions would have been exceedingly rare even in the early universe. It would make these early supermassive black holes flukes of nature cosmic accidents. Yet our observations suggest they were not rare at all. The James Webb Telescope is finding them with an almost alarming regularity, suggesting that whatever process created them was a robust common feature of the infant cosmos. Direct collapse, as beautiful a theory as it is, struggles to account for the sheer number of these impossible giants. The discrepancy has forced us to the edge of our cosmological understanding, pushing scientists toward a far more radical, far more unsettling possibility. We are staring at a locked-room mystery of cosmic proportions. The conventional methods of growth are too slow. The most promising shortcut seems too rare, too coincidental to be the universal answer. We have exhausted the standard playbook of astrophysics. So what if the answer isn't a faster way to grow a black hole, but an entirely different kind of object altogether? What if in the chaotic forge of the primordial universe, nature found a way to combine the two most powerful forces in the cosmos, the brilliant life-giving fire of a star and the insatiable light-devouring hunger of a black hole, into a single terrifying entity? What if, before the first true stars ever ignited their nuclear furnaces in the way we understand them, there was something else, a transitional object, a celestial chimera? This is the genesis of a truly mind-bending hypothesis, a concept that sounds like it was lifted from the pages of science fiction. The idea is that the first gargantuan structures to form in the universe were not stars in any conventional sense. They were something far larger, far brighter, and powered by a mechanism that defies our everyday experience of the cosmos. Imagine a colossal cloud of primordial gas, 1,000,000 times the mass of our Sun, collapsing under its own immense gravity. But instead of the core pressure igniting into a stable, self-sustaining nuclear fusion reaction, like it does in a normal star, the pressure and density become so extreme, so overwhelming, that the very centre of this embryonic object collapses first catastrophically into a nascent black hole. But this is not the end of the story. It is the beginning. The newly formed black hole, a seed of darkness now buried deep within the heart of its own parent cloud, is not isolated. It is surrounded by an unimaginable reservoir of fuel, the rest of the collapsing supergiant gaseous envelope. And so it begins to feed from inside. The black hole acts as a central engine, a voracious parasite consuming its host from within. The material of the collapsing cloud doesn't just fall freely, it churns and burns with incredible ferocity, as it is drawn toward the singularity, releasing a torrent of energy that pushes outward, halting any further collapse of the greater structure. This creates a bizarre temporary equilibrium. You have an object that looks from the outside like a star, a superluminous, impossibly massive star bloated to the size of our entire solar system, but its heart is not a furnace of fusion. Its heart is a growing abyss. It shines not with the light of creation, but with the light of annihilation. This theoretical object has a name that captures its strange paradoxical nature, a quasi-star. It is an object that is almost a star but is powered by a process that is the antithesis of a star. It is a celestial body whose luminosity is a direct consequence of the darkness growing at its core. This hypothesis offers a stunningly direct and violent solution to the paradox of the early giants. A quasi-star doesn't need to slowly accrete matter from the outside universe against the powerful headwind of the Eddington limit. Its fuel supply is its own body. The black hole inside can gorge itself, growing at a ferocious runaway rate, far exceeding any conventional limit because the gravitational prison of the star-like envelope contains both the fuel and the radiation. The black hole can swell from a mere 10 solar masses to tens of thousands, or even hundreds of thousands in the quasi-star's brief spectacular lifetime of only a few million years. Then, when the central engine has consumed enough of its host, the delicate balance is broken. The quasi-star dissipates its outer layers, blown away into space, revealing what it has been incubating all along, not a stellar remnant but a fully fledged intermediate mass black hole, ready and waiting in the dawn of the universe. It is a production line for exactly the kind of massive seeds needed to quickly grow into the billion solar mass monsters that haunt our deepest cosmic images. It is a theory born of desperation, a radical answer to an impossible question. It paints a picture of the early universe not as a gentle nursery, but as a cosmic laboratory, where the laws of physics experimented with forms of matter and energy that no longer exist today. These quasi-stars, if they were real, would be the missing link, the bridge between the first collapse of matter and the rise of the galactic empires ruled by supermassive black holes. They are the ghosts in the cosmic machine, the secret ingredient that could finally make our history of the universe make sense. But a theory, no matter how elegant, is not enough. We must ask, could such an object truly exist? What would it look like? And most importantly, is there any way we can find the fossil evidence of these long-vanished titans, these stars that were powered by their own internal black holes? The search for that evidence takes us deeper into the physics of the extreme, to the very limits of what we can imagine and what our telescopes can see. It is a hunt for the most spectacular monsters the universe has ever conceived. Is it possible for an empire to be built before its foundations are even laid? It's a paradox that defies logic, a timeline that feels fundamentally broken. Yet when we turn our telescopes toward the edge of observable reality, into the deepest recesses of cosmic time, we find exactly that. We find titans ruling over galaxies that were themselves just beginning to form gravitational monsters of impossible scale, dwelling in a universe that was by all accounts still in its infancy. This contradiction, this temporal impossibility, is not a minor footnote in the story of the cosmos. It is one of the most profound and unsettling mysteries in modern astrophysics, a puzzle that challenges the very narrative of how structure and how darkness itself first came to be. It begins, as so many cosmic tales do, not with a whisper, but with an impossibly bright scream across the void. These screams are the quasars. They are not stars, though for decades we thought they were. They are beacons of unimaginable power, celestial lighthouses shining from the farthest shores of space-time. A single quasar can outshine its entire host galaxy by a factor of thousands, blazing with the light of trillions of suns, yet all of this energy erupts from a region no larger than our own solar system. For something so compact to be so luminous, it must be powered by the most efficient engine nature has ever devised, matter being torn apart as it spirals into a supermassive black hole. The light we see is the death cry of gas and dust superheated to millions of degrees in a violent swirling disk, a final brilliant flare of defiance before being consumed forever. The quasar is the bonfire. The supermassive black hole is the furnace at its heart. And when we trace that ancient light back to its source, we are performing a kind of cosmic archaeology. Because the universe is so vast, light takes time to travel. The farther we look, the further back in time we see. The light from the Andromeda Galaxy, our nearest major galactic neighbour, is already 2.5 million years old. But the light from the most distant quasars began its journey long before that, when the universe was a fundamentally different place. This light has been travelling towards us for over 13 billion years, a ghostly message from a bygone epoch. Looking at these objects is like opening a time capsule from the cosmic dawn, the era when the very first stars were igniting and the first galaxies were coalescing from the primordial gloom. It is in this ancient nursery of the cosmos that we find the giants. Quasars like Ulysses J Thanathy 342+0928, whose light has travelled for 13.1 billion years, show us a universe just 690 million years old. At its core sits a black hole 800 million times more massive than our Sun. Even more extreme is the quasar J313-1806, a beacon from a time when the universe was a mere 670 million years young. The monster powering this object is staggering, tipping the cosmic scales at 1.6 billion solar masses. Let that sink in. Not a million, but over 1.5 billion times the mass of our star already fully formed and ferociously feeding at a time when the universe had lived less than 5% of its current lifespan. To put that into perspective, imagine the entire 13. 8 billion year history of the cosmos compressed into a single calendar year. The Big Bang happens in the first second of January 1st. On this scale, these billion sun-mass black holes are already in place and shining as colossal quasars by the third week of January. Humanity, by contrast, would not appear on the scene until the final few seconds before midnight on December 31st. How do you build something 1 billion times the mass of a star in what amounts to a cosmic blink of an eye? This is the crux of the problem what astronomers call the seed problem. You can't just have a giant, it must grow from something. But the timeline is so compressed, so brutally short, that our established understanding of how black holes form and grow begins to unravel completely. The cosmic recipe we have trusted for decades simply doesn't seem to work this early in the morning. Our standard time-tested recipe begins with stars. Specifically, it begins with the very first stars to ever exist. After the Big Bang, the universe was a remarkably simple place. There were no heavy elements, no carbon, no oxygen, no iron. There was only a vast expanding sea of hydrogen and helium, the raw materials forged in the initial fireball. Out of this pristine gas, under the gentle but inexorable pull of gravity, the first stars began to form. We call them population 3 stars, and they would have been unlike anything that exists in the universe today. Without the heavier elements that help cool modern star-forming clouds, the primordial gas clouds could not fragment easily. They just kept collapsing, growing larger and larger, until they ignited as solitary, magnificent behemoths. Imagine a star not 10, not 20, but hundreds of times the mass of our Sun. A blue-white giant blisteringly hot, burning through its hydrogen fuel with a fury that is difficult to comprehend. These were stars that lived fast and died young. A star like our Sun will burn for 10 billion years. A population 3 giant might last for only 2 or 3 million before its fuel was spent. Their existence was a brief incandescent flash in the primordial darkness, and their deaths were just as spectacular. Depending on their exact mass, they would have met one of two fates. Some would have exploded as supernovae of unimaginable violence, seeding the cosmos with the first heavy elements. But the most massive among them, those perhaps over 250 times the mass of the Sun, would have suffered a different fate. Their own gravity would have been so immense, so overwhelming, that not even a supernova explosion could stop their final collapse. They would have imploded, directly collapsing in on themselves without a whisper, their immense mass crushing down past any known point of resistance until they formed a black hole. This is the direct collapse model. These were the first black holes in the universe. They were the primordial seeds from which we assumed everything larger would grow, and they were impressive to be sure. A single one might have been born with a mass of 100, maybe 200 times that of our Sun. This seems like a promising start. You have a seed, and you have a target 1 billion solar masses. Now all you need is food and time. The early universe was gas-rich, a cosmic banquet for a nascent black hole. So the process should be simple. The seed black hole sits at the center of a protogalaxy, and its powerful gravity pulls in the surrounding hydrogen and helium, a process known as accretion. Like a whirlpool, it draws matter into a swirling, superheated disk. As the material spirals inwards, it releases enormous amounts of energy, the very light we see as a quasar before it crosses the event horizon, and adds to the black hole's mass. The more it eats, the more massive it gets. The more massive it gets, the stronger its gravitational pull becomes. The stronger its gravity, the more it can eat. It is a classic case of the rich getting richer, a runaway feedback loop of gravitational gluttony. On the surface, the path from 100 solar mass seed to a billion solar mass titan seems straightforward. You just need to keep the banquet going. But nature, it turns out, has a safety valve. There is a fundamental cosmic speed limit on how fast a black hole can grow a physical barrier that prevents it from consuming matter too quickly. And this is where our beautiful simple theory collides with the hard wall of physics. This barrier is known as the Eddington limit. It arises from a delicate cosmic balancing act. As matter falls towards a black hole, it doesn't just get hot. It radiates energy. It shines. This radiation, this intense light, carries momentum. It exerts a physical pressure, a gentle but persistent outward push on the very gas that is trying to fall in. Think of it like a wind blowing outward from the black hole. Gravity is pulling the gas in, but the light from the accretion disk is trying to push it away. If the black hole tries to feed too quickly, the accretion disk becomes so intensely bright that the outward pressure of its own light becomes overwhelming. It literally blows its food away, choking off its own supply. The Eddington limit defines the point of equilibrium, the maximum rate at which a black hole can accrete matter, before the radiation pressure halts the inflow. It's a natural thermostat, a cosmic throttle that dictates the ultimate speed limit for growth. And when we apply this speed limit to our problem, the timeline falls apart. Let's run the numbers on our most optimistic scenario. We start with a generous seed, a black hole of say 200 solar masses born from a giant population 3 star. We place it in the ideal environment, a constant, perfectly arranged supply of gas, allowing it to feed continuously at the absolute maximum rate allowed by the Eddington limit 24 hours a day for its entire life. Even under these impossibly perfect conditions for that 200 solar mass seed to grow into the 1.6 billion solar mass monster we see in quasar J0313 1806, it would require more time than the universe had to give, significantly more. By the time we observe that quasar at 670 million years after the Big Bang, our seed, even feeding at full throttle since the moment it was born, would barely have reached a few million solar masses. It wouldn't be a supermassive titan, it would still be a relative lightweight. We are off by orders of magnitude. The bank account shows $1 billion, but the pay stubs can only account for a few million. The math simply does not work. We have tried to find ways around it. Perhaps population 3 seeds were somehow much larger than we thought. Or perhaps multiple black holes formed and merged together in a rapid cosmic dance. But these scenarios require a chain of perfect circumstances, a series of cosmic coincidences, so unlikely that they verge on the fantastical. Mergers are inefficient, and assembling thousands of stellar mass black holes in one place so quickly in the chaotic environment of the early universe stretches credulity. The standard model, the elegant story of stellar birth, death, and gradual growth, is failing us. It provides the seeds, but it doesn't provide a viable path to the giants we see standing before us in the dawn of time. We are left with an undeniable observation and an inadequate explanation. The giants are real. Their presence is burned into the oldest light we can capture, yet the path to their creation appears to be a physical impossibility, a journey that required more time than the cosmos could offer. It's as if we've found a mountain range on a world that is too young to have experienced the geological forces required to build them. The discovery of these early quasars has created a crisis in cosmology, forcing us to confront a profound and unsettling possibility that we have been looking for the origins of these monsters in the wrong place entirely. Perhaps the first supermassive black holes didn't grow from the ashes of dead stars. Perhaps they required a different kind of birth. A birth not from a collapse into darkness, but from within a fire so immense it has no name and object of theory, so strange and so powerful it barely seems real. And so those ghostly red smudges of ancient light delivered to us by Webb's golden eye became more than just discoveries. They became accusations, each one a pinpoint of impossible mass glowing from the abyss of cosmic dawn, pointed an accusatory finger at the very foundations of our cosmic story. The smooth, elegant timeline we had written for the universe, a story of gradual evolution over billions of years, was suddenly riddled with paradoxes. These were not the infant black holes we expected to find tentatively sipping from the streams of primordial gas. They were titans fully formed, weighing in at millions, sometimes billions of times the mass of our own sun. And they were staring back at us from a time when the entire universe was barely a toddler less than 1 billion years old. The question was no longer if they existed. The question, a terrifying and thrilling one, was how? How could the universe build such monsters so quickly? To grasp the sheer scale of this cosmic conundrum, you first have to understand the conventional rulebook for building a black hole. For decades, the story was elegant, patient, and made perfect sense. It begins with the death of a truly colossal star, a star many times more massive than our Sun. In its final violent moments, its core collapses under its own stupendous gravity, crushing matter down beyond the point of no return. A black hole is born. But this newborn is a mere seed, perhaps 10, maybe 20 times the mass of the Sun. It is a formidable object to be sure, but it is a seed nonetheless. To grow into the supermassive behemoths we see at the hearts of galaxies like our own Milky Way, it needs to feed. It needs to accrete. Imagine this stellar mass seed adrift in the rich, chaotic environment of a young galaxy. It is surrounded by vast clouds of hydrogen gas, wandering stars, and a smorgasbord of cosmic debris. Its gravity is a relentless invisible tether, pulling this material inward. Gas and dust don't simply fall straight in. They're drawn into a spiraling dance of death, a flattened incandescent whirlpool of matter we call an accretion disk. Here, matter is accelerated to nearly the speed of light, compressed and superheated by unimaginable friction. This celestial mosh pit becomes the brightest thing in the universe, a quasar, a beacon shining across billions of light years. As matter from the inner edge of the disk finally loses its footing and crosses the event horizon, the black hole gains mass. It grows bite by bite over eons. This is the standard model, a slow, methodical feast, a process of patient accumulation where a black hole, like a celestial hermit, gradually integrates its surroundings into itself, growing ever larger, its gravitational influence spreading ever wider. Over the immense timescales of cosmic history, this process works beautifully. A stellar seed given a steady diet and 13 billion years can indeed swell into a monster weighing millions of suns. It's a story that fits perfectly with the galaxies we see in our local modern universe. The evidence is all around us. We see the accretion disks, we see the jets of energy they blast into space. We had, for all intents and purposes, solved the puzzle of their growth. We had written the biography of a black hole from its violent birth to its majestic galactic reign. But the light from the early universe changed everything. Those images from Webb weren't showing us the end of the story. They were showing us the preface, and the giants were already there. The timeline had been catastrophically compressed. The universe simply hadn't been around long enough for this slow, patient feeding to do the work. It was like finding a mighty oak tree centuries old in its girth and complexity, growing in a field that was ploughed only last week. The growth rate required was simply not possible. Something was fundamentally wrong with our story. The universe, it seemed, had a secret, a shortcut for creating giants, and it was a secret hidden in the physics of the feast itself. The problem, the great cosmic bottleneck that makes rapid growth so difficult, has a name: the Eddington limit. It is one of the most fundamental balancing acts in all of astrophysics, a point of perfect equilibrium between two of the universe's most powerful forces. On one side you have gravity, the relentless, indiscriminate pull of the black hole dragging matter inward. It wants nothing more than to consume everything to grow without limit. But on the other side you have light itself, not just the gentle light of a star, but the ferocious high-energy radiation, X-rays and gamma rays blasted out by that superheated accretion disk. This isn't just illumination, it is a physical force. Each particle of light, each photon carries momentum. And when you have a quasar blazing with the light of 1 trillion suns, that outward torrent of photons becomes a hurricane of pure energy. This blizzard of light slams into the infalling gas and dust, pushing it back. It is a form of radiation pressure, a celestial blowtorch trying to sterilize the black hole's immediate vicinity to starve it. The Eddington limit is the precise point where the inward crush of gravity is perfectly counteracted by the outward push of this radiation. If a black hole tries to feed too quickly, its accretion disk becomes so ferociously bright that it literally blows its own food away. It is a self-regulating mechanism, a natural governor built into the very fabric of physics that throttles a black hole's growth. It can only consume so much so fast before it chokes on the very brilliance of its own meal. Think of it like trying to pour sand into a powerful fan. A slow trickle might make it through, but if you dump the whole bucket at once, the wind from the fan will blow most of the sand right back in your face. The black hole is the fan, and its own blinding luminosity is the wind. This cosmic speed bump is the central villain in our story. It dictates the maximum possible rate of growth for any object accreting matter. And when astronomers sat down to do the math for the black holes Webb had discovered, the numbers didn't just disagree with the theory, they staged a rebellion. Let us trace the impossible arithmetic. We start with a generous seed, a black hole born from the first generation of stars weighing perhaps 100 times the mass of our Sun. A true heavyweight for its era. Now we allow it to feed. We place it in the richest, most gas-dense environment the early universe has to offer. And we let it consume material at the absolute, physically allowed maximum, the Eddington limit without interruption, for every single second of its existence. We give it the most optimistic perfect conditions imaginable. Even under this dream scenario, for that 100 solar mass seed to grow into a billion solar mass Titan would require it to continuously double its mass in what is known as the Salpeter timescale, roughly every 45 million years. The problem is when we see a billion solar mass black hole just 700 million years after the Big Bang, the clock has already run out. There simply haven't been enough of these doubling times to get the job done. In fact, it's not even close. The black hole would need to have been feeding at its absolute maximum rate since before the first stars had even ignited. It would need to have started growing before there was anything for it to eat. The timeline is broken. The math fails, and it fails spectacularly. It's like asking a single bacterium to evolve into a blue whale in 3 days. The underlying biological processes are sound, but the timescale makes a mockery of the claim. Scientists faced with this contradiction tried desperately to find a way around it. Perhaps they theorized accretion could be super Eddington. Maybe under certain conditions the infilling gas is not uniform. If it's clumpy and dense, some of it might be able to punch through the wall of radiation like cannonballs through a gale-force wind. This clumpy accretion could in theory allow a black hole to exceed its speed limit, but only for brief violent spurts. It couldn't sustain this binge eating for hundreds of millions of years. Others proposed that maybe the accretion disks were different, somehow less efficient at producing radiation. If the disk was slim, allowing some energy to be advected or swallowed by the black hole instead of radiating away, that might also raise the ceiling for growth. But each of these solutions felt like a patch, a desperate tweak to a model that was fundamentally cracking under the weight of new evidence. They could perhaps explain a black hole that was twice as big as expected, or maybe even 10 times as big. But they could not explain the monsters that were 1,000 times more massive than they had any right to be. These were not mere anomalies that could be explained by a clever workaround. They were fundamental challenges to our understanding. The universe wasn't just bending the rules of black hole growth, it was playing an entirely different game. The inescapable conclusion began to dawn on the astronomical community. Maybe the problem wasn't with the growth. Maybe the problem was with the seed. The entire edifice of the standard model was built on the assumption that supermassive black holes start small as the stellar mass remnants of dead stars. But what if they didn't? What if the universe had a way to skip the first, most tedious steps of this process? What if it could build a far, far more massive seed from the very beginning? This was a radical departure, a line of thinking that forced astronomers to journey back even further in time, back to an era before the first stars had ever shone, when the universe was a far simpler, more elemental place. A place filled with nothing but unfathomable oceans of hydrogen and helium gas, bathed in the fading afterglow of the Big Bang itself. This new idea was given a suitably dramatic name, the direct collapse model. It proposed that under a very specific and very rare set of primordial conditions, a supermassive black hole could be born without a star ever having to die. The theory required a truly monolithic cloud of pristine primordial gas. By pristine, we mean a cloud utterly untouched by the heavy elements, the carbon, oxygen, and iron that are forged in the hearts of stars and scattered through space when they die. These heavy elements are crucial. They act as powerful coolants, allowing a giant gas cloud to radiate away its heat fragment into countless smaller clumps and form a bustling cluster of normal stars. A cloud of pure hydrogen and helium, however, is terrible at cooling itself. It doesn't have these chemical tools, So imagine such a cloud, a vast quiescent reservoir of primordial gas, 1,000,000 times the mass of our Sun. It is a cloud that cannot fragment. It cannot collapse into 1,000 points of light. Instead, bathed in the ultraviolet radiation from a nearby nascent galaxy. Radiation that suppresses any rogue star formation, the entire monumental object begins to contract under its own immense gravity. There is no fragmentation, no stellar nursery. There is only a single catastrophic, all-encompassing collapse. The entire cloud, 1,000,000 suns worth of matter, plunges inward toward a single point. It is not forming a star. It is forming something far larger, far more dense, a temporary supermassive object that is destined to collapse completely. The result of this direct monolithic implosion would not be a 10 solar mass black hole. It would be a seed weighing 100,000, perhaps even 1,000,000 times the mass of the Sun. An intermediate mass black hole born in a single spectacular event. This wasn't just a bigger seed, it was a quantum leap. It was like starting a marathon 20 miles past the starting line. With a seed this massive, the impossible arithmetic of the Eddington limit suddenly became plausible. Given this colossal head start, even a steady law-abiding rate of accretion could be enough to grow 1,000,000,000 solar mass quasar in the time allotted. The direct collapse model provided a beautiful if exotic potential solution. It redrew the cosmic family tree, suggesting that the biggest black holes weren't simply the descendants of the first stars, but a different kind of primordial beast altogether, born from the raw, unadulterated stuff of the Big Bang. It was a breathtaking theory, a testament to the ingenuity of the human mind when confronted with the seemingly impossible. It painted a vivid picture of the cosmic dawn, a time of titanic forces and singular events that have no parallel in the modern universe. For a time, it seemed that the mystery might be solved. The direct collapse black hole became the leading candidate, the great hope for explaining away the paradox that Webb had laid bare. Yet even this elegant and powerful idea began to show its own cracks. The conditions required are incredibly precise, almost unnervingly so. You need a massive pristine cloud, and you need it to be irradiated by just the right amount of light from a neighbouring galaxy, too little, and it forms stars, too much, and the gas is blown away entirely. These Goldilocks conditions meant that such events would be exceptionally rare. Could they have been common enough to explain the sheer number of supermassive black holes we now see dotting the early cosmos? The models grew more complex, the debates more intense, and a deeper, more troubling question emerged from the heart of the direct collapse theory itself. As that 1,000,000 solar mass cloud of gas collapses, what does it actually form during the collapse? It doesn't just instantly become a black hole. Physics demands a transitional state. An object of unimaginable size and luminosity must exist, however briefly, before the final irreversible plunge into a singularity. The inward crush of gravity and the outward pressure of the heat generated by that collapse would fight a ferocious battle. Astrophysicists realized they were contemplating an object that had until now lived only in the wildest realms of theoretical physics. A star of impossible proportions powered not by nuclear fusion in its core, but by the gravitational collapse of its own substance. A star with a mass of 1,000,000 suns so large and luminous it would defy all known categories. They had a name for this hypothetical object, a name that evoked its strange paradoxical nature, and as they explored its properties they began to wonder if they had stumbled upon something even more profound. What if the crucial step wasn't just the collapse itself? What if the secret to building a monster was hidden inside the heart of this temporary unbelievable star? The stage was now set. The limitations of conventional growth had driven us to the brink of a new cosmology, forcing us to imagine objects of unprecedented scale. But to truly solve the puzzle, we would have to dare to look inside one of these nascent giants to ask what happens when a star grows so large that it collapses from within, and in its core a black hole begins to stir. The aporia of direct collapse, the maddening puzzle of a universe that needed giants, but seemingly forbade their direct creation, left cosmology at an impasse. The models were elegant, the physics sound, yet they kept breaking against the stubborn realities of angular momentum and fragmentation. The universe, it seemed, refused to build its great gravitational anchors in a single magnificent stroke, and so for a time the mystery of the first quasars deepened, their impossible light taunting us from the dawn of time. But what if the question itself was framed incorrectly? What if we were trying to solve the problem from the outside in? In the quiet halls of theoretical physics, a new, almost heretical idea began to take shape. It was a whisper that grew into a paradigm-shifting theory, an answer so counterintuitive, so bizarre, that it could only have been born from the extreme physics of that primordial age. The solution wasn't to force a titanic cloud of gas to become a black hole. The solution was to assume a black hole was already there, waiting at the heart of the storm. This was the birth of the quasi-star, a theoretical object of such staggering proportions and alien mechanics that it challenges our very definition of what a star can be. Forget the familiar nuclear furnaces that populate our modern cosmos. Forget the gentle twinkle of stars like our sun. You must instead imagine a structure not of stellar mass but of galactic mass, a behemoth born in the cradle of the first dark matter halos. Picture a cloud of pure, pristine hydrogen and helium, untouched by the heavy elements forged in later stellar generations. This is not a cloud destined to form a star cluster. It is a single coherent object containing the mass of millions of suns, a vast, slowly contracting sea of primordial gas. Under the relentless crush of its own gravity, this protogalactic nebula begins to fall inward, a cascade of matter, on a scale we can barely comprehend, seemingly destined to collapse into a single hypermassive black hole. But at its core, hidden deep within the swirling maelstrom, something is already present. A seed. The seed is a small stellar mass black hole, perhaps only 10 or 20 times the mass of our Sun. It might be the lonely remnant of one of the very first population 3 stars, a true first-generation titan that lived fast and died young, leaving behind a compact singularity. This tiny gravitational anchor, a mere speck adrift in an ocean of collapsing gas, becomes the protagonist in our story. As the colossal envelope of gas plummets towards the centre, it doesn't simply crash into a point. Instead, it finds this pre-existing black hole. And in that moment, the entire dynamic of the collapse is irrevocably altered. A new engine ignites, one fueled not by nuclear fusion, but by the raw, untamed power of gravity itself. The gas now swirling into a ferociously hot and dense accretion disk around the black hole begins to be consumed, and the process of a black hole feeding is the most efficient energy generation mechanism known to physics. As matter is torn apart, accelerated to near the speed of light and crushed by unimaginable tidal forces, just before crossing the event horizon, it doesn't vanish silently. It screams, it radiates, it unleashes a torrent of energy, a blast of light and heat so intense it beggars belief. This is the central furnace of the quasi-star, a captive quasar roaring in its heart. The sheer luminosity generated by this tiny feeding black hole is staggering, a celestial blowtorch that begins to push outwards with incredible force. This outward push is called radiation pressure, the physical momentum imparted by countless photons striking the surrounding gas. Suddenly, there are two fundamental forces at war within this leviathan. There is the crushing inward pull of gravity from the millions of solar masses of the gas envelope, a force determined to complete the collapse. And now there is the violent outward push of the light from the accreting central engine, a force fighting desperately for equilibrium. When these two colossal forces meet, a state of near-perfect balance can be achieved. The inward gravitational crush is precisely counteracted by the outward radiation pressure. The collapse halts, the structure stabilizes. It doesn't fly apart, nor does it immediately shrink into a black hole. It simply hangs there, suspended in a delicate cosmic truce. This is the quasi-star, an object that looks from the outside like an impossibly luminous supergiant star, perhaps as large as our entire solar system, with a surface temperature cooler than our sun's, glowing a dull, menacing red. But its appearance is a profound deception, for this is not a star at all. It is a bloated, incandescent envelope of gas, a temporary cosmic vessel, whose entire existence is predicated on containing and regulating the immense power of a feeding black hole at its core. It is in essence a star powered by a black hole heart. This revolutionary concept resolves the problems that plagued the direct collapse model. The pre-existing black hole seed provides the central mass concentration needed to organize the collapse, while the feedback from its accretion prevents the catastrophic fragmentation that would otherwise shatter the cloud into a swarm of smaller stars. The quasi-star is a self-regulating machine. If gravity begins to win, and the envelope compresses further, the density of gas around the central black hole increases. This in turn boosts the accretion rate, causing the black hole to feed more voraciously. The energy output skyrockets, the radiation pressure intensifies, and the envelope is pushed back outwards, restoring the equilibrium. Conversely, if the radiation pressure becomes too dominant, and the envelope begins to expand, the gas density at the core drops. The black hole's fuel supply dwindles, its energy output fades, and gravity reasserts its dominance, pulling the envelope back inward. This delicate dance can in theory persist for millions of years, a crucial window of time in the early universe. To truly grasp the alien nature of a quasi-star, we must meticulously distinguish it from anything that exists today. It is fundamentally irreconcilably different from a normal fusion-powered star. Our Sun, like all its stellar kin, generates energy through thermonuclear fusion. In its core, under immense pressure and temperature, hydrogen nuclei are fused together to form helium, releasing a tiny fraction of their mass as energy according to Einstein's famous equation E = mc². It is a process of creation of building heavier elements from lighter ones. The core of a fusion-powered star is a furnace of nuclear creation. The heart of a quasi-star is the opposite. It is a place of ultimate annihilation, a singularity. Its energy is not generated by creating new elements, but by consuming matter, entirely converting gravitational potential energy into radiation with terrifying efficiency. A fusion star is a controlled, long-lived nuclear reactor. A quasi-star is a tamed gravitational bomb, a pressure cooker containing the most violent process in the cosmos. One could draw an analogy. A conventional star is like a vast, slow-burning forest fire consuming its fuel log by log over billions of years. A quasi-star, on the other hand, is like the continuous directed exhaust of a rocket engine, its power derived from the controlled funneling of a massive fuel source into a tiny combustion chamber. The scales are also profoundly different. The most massive stars we know of today might reach a few hundred solar masses. A quasi-star begins at 1,000, and more likely contains the mass of millions of suns, making it more akin to a small galaxy than a large star. Its lifespan is also a mere flicker in cosmic time, a few million years at most, compared to the billions of years our Sun will enjoy. It is a fleeting transitional phase, a glorious but temporary solution to a cosmic engineering problem. There is another more obscure theoretical object that invites comparison, the Thorne-Jitkov object. First proposed in the 1970s, a Thorne-Jitkov object, or TZO, is a hypothesized hybrid star where a neutron star, the ultra-dense remnant of a supernova, has been consumed by a red giant companion. In this scenario, the neutron star spirals into the core of the red giant and replaces the giant's original core. The entire bloated, gaseous envelope of the red giant is then supported by the heat and exotic nuclear reactions generated on the surface of this embedded neutron star. At a superficial level, the concept sounds strikingly similar to a quasi-star, a compact object powering a large diffuse envelope. Yet the two are worlds apart, separated by 13 billion years of cosmic evolution and fundamentally different physics. The core of a TZO is a neutron star, a ball of degenerate neutron matter about the size of a city, but with more mass than our Sun. The core of a quasi-star is a black hole, a true singularity with an event horizon from which nothing can escape. This is not a subtle distinction. It is the most profound difference imaginable. The energy from a TZO's core comes from a combination of accretion onto the neutron star's surface and unique nucleosynthesis pathways, a process far less efficient than accretion onto a black hole. Consequently, a TZO would be far less luminous and massive than a quasi-star. Most critically, TZOs are a theoretical possibility in our modern universe, formed from the interactions of evolved ancient stars rich in heavy elements. They are a rare cosmic curiosity, a potential outcome for specific binary star systems in a mature galaxy. Quasi-stars, by contrast, are primordial phantoms. Their existence is inextricably tied to the unique and unrepeatable conditions of the cosmic dawn. They could only form from the collapse of those first gargantuan clouds of pristine hydrogen and helium. The gas had to be metal-free. Metals, the heavier elements cooked in the hearts of stars, are incredibly efficient coolants. If the collapsing cloud had been seeded with even a small fraction of carbon or oxygen, the gas would have cooled far too rapidly, fragmenting into countless smaller clumps and forming a star cluster instead of a single monolithic object. The environment had to be one of raw, untamed potential before the universe had been polluted by the ashes of its first stellar creations. They belonged to an era before galaxies as we know them had fully formed, existing as the luminous, monstrous hearts of the first protogalactic halos. They are not an oddity of stellar evolution. They are a proposed necessary step in the evolution of cosmic structure itself. They are the missing link, the bridge between the first small black holes and the supermassive giants that would come to dominate the centres of all major galaxies, including our own Milky Way. The quasi-star, therefore, is not an end in itself. It is a way station. It is a cosmic nursery for a growing black hole. Inside this vast luminous cocoon, the central black hole is not static. It is constantly feeding steadily and voraciously from the inner layers of its gaseous envelope. With every particle it consumes, it grows more massive, its gravitational influence expanding, its event horizon swelling. A black hole that began as a mere 10 solar masses could, over the course of 1,000,000 years, grow to 1,000 or even 10,000 solar masses. It is a period of spectacular accelerated growth hidden from the rest of the universe beneath a glowing shroud. The quasi-star provides the perfect incubator, a stable, high-pressure environment with a continuous supply of fuel, allowing its central engine to bulk up at a rate that would be impossible in the cold vacuum of open space. It solves the timescale problem by creating a system that force-feeds a black hole seed, transforming it into an intermediate mass black hole in a geological blink of an eye. This was the beautiful, terrifying solution that theorists proposed. A celestial object that lived a brief, brilliant life, acting as a crucial stepping stone on the path to galactic monarchy. It was a bridge across the chasm of mass connecting the stellar to the supermassive, but like all bridges, its purpose is to be crossed. This delicate equilibrium, this standoff between light and gravity, could not last forever. The very process that sustains the quasi-star is also the architect of its doom. The central black hole, growing ever more massive and powerful, is steadily changing the fundamental parameters of the entire system. What happens then when the engine at the heart of this star grows too powerful? What happens when the mass of the black hole becomes too great for the envelope to contain? The story of the quasi-star is not just the story of its life, but also the story of its inevitable cataclysmic death, a final, spectacular act that would forever change its corner of the young universe. But to bring such an impossible creature from the realm of pure imagination and into the rigorous world of physics requires a descent into a computational maelstrom. The very idea, a star powered not by nuclear fusion, but by the gravitational fury of a captive black hole, is a paradox wrapped in plasma. How could such a thing even hold itself together? How could a celestial body 10,000 times the mass of our Sun, inflated to the size of a solar system, avoid simply tearing itself apart under its own contradictory impulses? The answer lies in a delicate, violent, and utterly astonishing balancing act, a cosmic tightrope walk performed over a gravitational abyss. Inside the heart of the quasi-star, two primordial forces are locked in an eternal war. At the very centre, you have the insatiable appetite of the burgeoning black hole. It is not a static object. It is an engine of consumption, relentlessly pulling in the dense, superheated gas of the star's inner layers. Each particle that crosses its event horizon releases a torrent of energy, a final, brilliant scream of light and heat as it's ripped from existence. This is accretion power, the most efficient energy generation process known to science, and it provides a colossal upward pressure, a celestial blowtorch aimed at the star's own core. This outward blast of radiation is the quasi-star's salvation and its torment. It acts as a support system, a pillar of pure light holding up the unimaginable weight of the star's gaseous envelope. Without this constant, violent outflow, the entire structure, all billion miles of it, would collapse in on itself in a heartbeat, feeding the central monster until it became a supermassive black hole in a flash of cosmic annihilation. Yet this very same radiation pressure is what chokes the black hole's food supply. It pushes back against the infalling gas, threatening to starve the very engine that keeps the entire edifice from imploding. The quasi-star therefore must live its entire fleeting life teetering on a knife's edge. Astrophysicists call this precarious equilibrium the Eddington limit. Think of it as a fundamental speed limit on how fast a black hole can eat. If it consumes matter too quickly, the resulting blast of energy is so intense, it blows away any more incoming fuel, effectively shutting down the meal. A normal accreting black hole flickers and sputters as it hits this limit. But the quasi-star is different. Its immense bloated envelope acts as a colossal pressure vessel, a gravitational clamp that forces gas downward, constantly trying to overwhelm the Eddington limit and feed the singularity. To model this extraordinary state of affairs is one of the great challenges in modern astrophysics. You can't just use the equations that govern a normal star like our Sun. The physics are utterly alien. The core isn't a furnace of fusion, it's a gravitational vortex. The energy doesn't percolate gently outwards over 1 million years. It erupts from a central point source with unimaginable ferocity. Scientists must build their simulations from the ground up, combining the laws of general relativity that govern the black hole with the principles of hydrodynamics that describe the churning, boiling ocean of gas that surrounds it. These models reveal an object of almost unimaginable complexity. The quasi-star's envelope wouldn't be a smooth, placid sphere. It would be a seething cauldron of convection cells the size of entire star systems. Plumes of superheated gas energized by the black hole's radiation would rise like titanic thunderheads through the star's atmosphere. Cooler, denser gas from the outer layers would then plunge inward to take their place, creating a perpetual churning motion that constantly dredges material down toward the hungry core. It's a self-regulating, self-destructive machine. The black hole grows, its energy output increases, the convection becomes more violent, and the entire structure swells all while its own gravity tries to crush it into nothing. The sheer scale of this process is difficult to comprehend. The light generated at the core does not travel freely. It must fight its way through a thick, soupy fog of primordial hydrogen and helium. For this light, the journey from the central engine to the surface is a chaotic battle. It's absorbed by one atom, re-emitted in a random direction, only to be absorbed by another 1 billion times over. This random walk transforms the high-energy X-rays and gamma rays from the accretion disk into a flood of comparatively cooler visible light by the time it reaches the surface. The quasi-star's brilliant glow is therefore not the direct light of its engine, but a filtered thermal echo of the violence hidden within. And it is this filtering mechanism, this suffocating cloak of gas, that allows the quasi-star to perform its greatest trick, cheating the Eddington limit. Because the envelope is so opaque and turbulent, the radiation can't escape efficiently. It gets trapped, building up a pressure that inflates the star like a balloon. This internal pressure helps to support the star's weight, but it also allows the black hole to consume matter at a rate that would otherwise be impossible, a super Eddington accretion flow that fuels its rapid, relentless growth. It is a cosmic loophole, one that allows a black hole to gain mass at a ferocious pace, hidden from the universe inside its own stellar incubator. But this cosmic balancing act cannot last forever. Nothing this violent, this contradictory, is built to endure. The models predict a lifespan for a quasi-star of only a few million years. In the grand timeline of the cosmos, this is a vanishingly brief moment, the flicker of a match in the dark. For comparison, our own Sun is expected to live for 10 billion years. The entire reign of a quasi-star, an object that could potentially birth a galaxy-anchoring black hole, is shorter than the time it took for humanity's ancestors to evolve from walking on 4 legs to 2. Its death is written into its very architecture. Every second of its existence, the central black hole grows more massive, as it swells from an initial seed of a few dozen solar masses to thousands and then tens of thousands. Its gravitational influence begins to overpower the delicate equilibrium. The accretion becomes more efficient, the energy output more extreme. The star's outer layers are heated to such an incredible degree that they begin to boil away into space. The quasi-star begins to evaporate, shedding its own substance in a slow, inexorable self-destruction. Finally, a tipping point is reached. The black hole's gravitational pull becomes so dominant, and the gaseous envelope has been so depleted that the remaining structure can no longer be supported. The outward push of radiation finally wins the war. In a final gargantuan sigh, the quasi-star blows its remaining atmosphere away, dispersing trillions of tons of hydrogen and helium into the void. The stellar cloak is thrown off, and for the first time the black hole at its heart is revealed to the universe. A new monster is born, an intermediate mass black hole now naked and adrift in the dark, ready to begin its long journey of growth toward becoming a true supermassive behemoth. This short dramatic life presents astronomers with a profound problem. If quasi-stars only existed for a few million years in the first few 100 million years of the universe's history, what are the chances we could ever see one? The cosmic dawn is a murky, distant era, its light stretched and dimmed by 13 billion years of travel. Finding a specific transient object within that faint glow is like trying to spot a single firefly in a fog bank from 100 miles away. We are searching for ghosts in the oldest light in the universe. The challenge is compounded by a frustrating case of cosmic mistaken identity. From our immense distance, what would a quasi-star even look like? The models predict a surface temperature of only a few thousand degrees, not much hotter than the coolest red giant stars in our own galaxy today. This means that despite its internal fury, its outward appearance would be a deceptively gentle reddish light. It would be a colossal, superluminous but relatively cool object. The problem is the early universe was likely filled with other kinds of bright objects. How would you distinguish the unique light of a quasi-star from, for instance, a pristine, first-generation galaxy undergoing a massive burst of star formation? Both phenomena would be enormous, incredibly bright, and located in the same dense, gas-rich environments. Their light signatures, their spectra, might be maddeningly similar. The spectral lines of hydrogen and helium, the key chemical fingerprints astronomers use to identify objects, would be present in both. Disentangling the signal of one from the other would require observations of exquisite precision, pushing our best telescopes like the James Webb Space Telescope to the absolute limits of their capabilities. We are looking for a whisper in a cosmic symphony, a subtle anomaly in the light that might betray the presence of a gravitational engine hidden within a stellar shroud. This profound difficulty has fueled one of the most intense and fascinating debates in modern cosmology, because the quasi-star is not the only suspect in the mystery of how supermassive black holes got so big so fast. There is another competing theory, a rival narrative that offers a more direct, though no less dramatic path to creating a giant. This is the theory of direct collapse black holes. Imagine, if you will, not a single colossal star, but an entire primordial cloud of gas, a vast, turbulent nebula containing the mass of 100,000 suns. In this scenario, the cloud is so massive and so pure, containing almost none of the heavier elements that help gas to cool and fragment, that it does something extraordinary. It bypasses the entire process of star formation. There is no protostar, no fusion, no stellar intermediary. The cloud's own gravity is so overwhelming that it collapses in on itself in a single catastrophic event, a gravitational avalanche of cosmic proportions. The core of the cloud becomes so dense, so compressed, that it implodes directly into a black hole, forming a seed of tens of thousands of solar masses in one fell swoop. This direct collapse model is in many ways a more brutally efficient solution to the problem. It skips the delicate, unstable, and brief quasi-star phase entirely. It provides the early universe with a substantial black hole seed almost instantaneously, giving it a crucial head start in the race to become a billion solar mass titan. To its proponents, it feels like a cleaner, more elegant explanation, a cosmic shortcut that avoids the baroque complexities of a star powered by a black hole. They argue that the conditions in the early universe, with vast reservoirs of pristine gas, were perfect for just such a cataclysmic event. The debate between the quasi-star and direct collapse camps is a battle fought not with telescopes but with supercomputers. Each side runs incredibly sophisticated simulations testing their models against the fundamental laws of physics and the few observational constraints we have from the early cosmos. Is it more likely for a single protostar to capture a black hole and swell into a quasi-star? Or is it more plausible for a massive gas cloud to resist fragmentation and collapse in its entirety? The answer depends on a dizzying array of factors: the precise temperature of the primordial gas, the strength of interstellar magnetic fields, the level of turbulence, and the subtle influence of dark matter, halos pulling everything together. It is a theoretical deadlock. Both scenarios appear plausible under certain specific and very rare conditions. It may well be that the universe used both methods, creating black hole seeds through multiple pathways depending on the local environment. Perhaps quasi-stars formed in the hearts of the very densest, most compact protogalaxies, while direct collapse occurred in more massive sprawling filaments of gas. The universe is rarely simple, and it often has more than one way of building its most magnificent structures. But without a definitive observation, without what astronomers call a smoking gun, the origin of the first supermassive black holes remains a profound and tantalizing mystery. So if we can't see a quasi-star directly, and the theory is locked in a debate with a powerful rival, where do we go from here? We must become cosmic detectives, searching not for the object itself, but for the clues it may have left behind. We hunt for its echoes, the indelible fingerprints that its brief, violent life may have imprinted on the cosmos. This search pushes us beyond simply capturing light into the new frontiers of astronomy. One of the most promising avenues is the search for gravitational waves. When a quasi-star finally dies and its central black hole is set free, what happens next? These newly formed black holes with masses of thousands of suns would not remain isolated for long. They would exist in the crowded, chaotic nurseries of the first galaxies, and they would inevitably find each other. Their gravitational dance would be spectacular, a slow spiral inwards over millions of years, culminating in a cataclysmic merger that would shake the very fabric of space-time. This merger would release a burst of gravitational waves ripples in reality, of a frequency and amplitude our current detectors are not yet sensitive enough to see. But future observatories like the planned Laser Interferometer Space Antenna or LISA are being designed specifically to listen for this low-frequency hum of the early universe. If LISA were to detect a chorus of mergers between black holes of 10,000 solar masses, it would be powerful circumstantial evidence for the quasi-star model. It would tell us that the universe was proficient at creating black holes of that specific intermediate size, a key prediction that distinguishes it from the direct collapse scenario. Another potential clue lies in chemistry. The gargantuan envelope of a quasi-star processed by the intense radiation of its central engine and then cast out into the void would be chemically unique. It would carry a distinct signature, an enrichment of certain elements that could seed the surrounding interstellar gas. If we could find ancient metal-poor star systems today that show this peculiar chemical abundance pattern, it might be like finding a fossil, a remnant of the long-vanished ecosystem that was dominated by these strange temporary suns. And finally, the evidence may lie hidden in plain sight in the population of supermassive black holes we see today. The two formation channels, quasi-stars and direct collapse, might produce black holes with subtly different characteristics, different initial spins or a different distribution of masses. By taking a precise census of the black holes in the local universe and tracing their growth backwards through time with our simulations, we might be able to discern which starting condition, which type of seed, provides a better fit for the cosmic giants that rule the galaxies today. The answer to a question about the dawn of time may be locked away in the dynamics of galaxies that are our cosmic neighbours. The quest to understand these theoretical titans is more than just an academic exercise. It forces us to confront the limits of our knowledge, to imagine objects that operate under a physics so extreme it verges on the magical. The quasi-star remains a phantom, a creature of pure theory, born from the tension between gravity's ultimate triumph, the black hole and the radiant defiance of a star. It is a testament to nature's ingenuity, a reminder that the universe may have built its most enduring monuments using tools we're only just beginning to imagine. And our search for it, a hunt for a ghost in the machine of the cosmos, continues. And so we arrive at the very heart of the paradox, the magnificent self-defeating violence of a nascent black hole. We have witnessed the cosmic standoff, the insatiable hunger of a gravitational point of no return pitted against the furious gale of its own incandescent leftovers. For a naked black hole floating alone in the primordial void, this is an unbreakable law. Every particle it devours unleashes a torrent of high-energy photons, a radiant hurricane that blasts away the very cosmic filaments meant to be its next meal. This is the Eddington limit, not merely a guideline, but a physical barrier etched into the fabric of space-time, a cosmic speed limit on growth. It is the universe's own elegant, frustrating system of checks and balances, ensuring that no single object can grow too quickly. A black hole on this enforced starvation diet might double its mass in 100 million years, a glacial pace in the frantic dawn of the cosmos. But the monsters we see today, the supermassive titans governing the hearts of galaxies, were already giants when the universe was but a toddler. They did not have the luxury of time. They could not have obeyed this law. This glaring discrepancy, this impossible growth spurt, has haunted astrophysicists for decades, standing as one of the great unsolved puzzles of our cosmic origin story. There had to be another way, a hidden pathway, a loophole in the cosmic rulebook that allowed the first black holes to bypass this fundamental constraint. The quasi-star, this phantom object of theory and simulation, is not just a candidate for that loophole. It is the master key designed by the universe itself to unlock explosive runaway growth. The secret lies not within the black hole at its core, but in the colossal, swaddling atmosphere that surrounds it, the very envelope that makes it a quasi-star. This gargantuan shroud of primordial hydrogen and helium, stretching for billions of kilometers, becomes the ultimate accomplice in the black hole's cosmic heist. It is a shield, a buffer, and a fuel tank, all rolled into one monolithic turbulent sphere. Its function is deceptively simple, yet its consequences are profound. It is engineered to smother the black hole's cry of light. As the central engine gorges on the innermost layers of gas, the resulting blast of radiation, that photonic hurricane that should have sterilized the surrounding space, erupts outwards. But it never reaches the vast cool reservoir of gas in the proto-galaxy beyond. Instead, it smashes headlong into the dense inner wall of the quasi-star's own envelope. The light doesn't escape. It is caught trapped within a prison of its own making. The envelope, trillions upon trillions of kilometers thick, is almost perfectly opaque. It absorbs this ferocious energy not as a solid wall would, but like a colossal cosmic sponge. The high-energy X-rays and ultraviolet photons are thermalized, their fierce directed power converted into a more gentle diffuse heat that spreads throughout the entire volume of the star-like object. The celestial blowtorch at the center is transformed into a slow, radiant glow at the surface. From the outside, you would not see the raging violence of a feeding black hole. You would see what appears to be an impossibly luminous, yet relatively cool supergiant star. The evidence of the crime is completely hidden from view. This act of concealment is the critical first step. By trapping the radiation, the envelope effectively dismantles the Eddington limit for the black hole itself. The outward push of light is no longer a factor in the wider environment. With the photonic shield down, the path is cleared. Now gravity, relentless and unopposed, can truly take command. The quasi-star's own monolithic gravitational field continues to pull relentlessly on the pristine gas clouds of the young galaxy in which it resides. Vast cold rivers of primordial matter, unhindered by any repulsive force, begin a slow, inexorable journey inward, streaming toward the surface of this bloated cosmic behemoth. They are drawn in not to feed the black hole directly, but to replenish the very envelope that serves as its shield and larder. The quasi-star grows its mass piling on from the outside, maintaining the immense pressure needed to sustain its paradoxical structure. It becomes a gravitational anchor, a cosmic nexus point channeling the raw material of the infant universe into a single focused location. And inside this celestial pressure cooker, the true miracle of growth begins. The process is not a gentle rain of matter, but a chaotic, turbulent cascade. Imagine a parcel of hydrogen gas drawn from the outer darkness, crossing the photosphere of the quasi-star. It is now inside the machine. It joins a churning convective interior, a realm of unimaginable pressures and temperatures far hotter than the core of our own sun. Here it is caught in immense slow-moving currents driven by the very heat bleeding from the black hole's accretion disk far below. For millennia, this parcel of gas will be dragged down, then churned back up, mixing and mingling in a violent ballet that spans a volume larger than our solar system. The entire envelope acts as a colossal buffer, regulating the flow of fuel. It ensures the black hole is not overwhelmed and choked, nor is it starved. It mediates a flow rate that would be physically impossible in a naked environment. Slowly, inevitably, our parcel of gas is dragged deeper and deeper into the gravitational well. The pressure mounts to astronomical levels, the temperature soars. Finally, after its long journey through the churning interior, it reaches the final frontier, the boundary of the black hole's own accretion disk. Here it is torn apart by tidal forces, its atoms stripped of their electrons, forming a swirling vortex of incandescent plasma. This is the point of no return, the final frantic spiral into oblivion. And as it falls, it releases a final brilliant burst of energy, the very radiation that will be caught by the layers of gas above it, perpetuating the cycle that allows its brethren to follow the same one-way path. The envelope doesn't just allow for feeding, it enables a relentless super Eddington deluge. While a normal black hole is limited to sipping matter through a cosmic straw, the quasi-star allows its central engine to open a fire hose funneling material inward at a rate hundreds, even thousands of times greater than previously thought possible. The numbers predicted by the theoretical models and supercomputer simulations are simply staggering, representing a mode of growth so extreme it rewrites the story of cosmic dawn. A seed black hole beginning at a respectable but not extraordinary 10 or 20 times the mass of our Sun finds itself at the heart of this perfect feeding machine. Within the quasi-star's nurturing cocoon, it begins to swell at a precipitous rate. In just 10,000 years, a blink of an eye in cosmic terms, it can grow to 1,000 solar masses. After 100,000 years, it might surpass 10,000 solar masses. The simulations, which tax the most powerful computational systems on Earth, show this process in breathtaking detail. We can watch as the quasi-star flickers and breathes its outer layers, pulsating as vast quantities of gas are dumped onto it, causing the entire structure to swell and contract. We can witness the violent flickering radiation from the core fighting against the crushing weight of the envelope, a battle of forces that sustains this impossible object. The computer models allow us to peel back the layers to see the intricate dance of physics that makes this all possible. We see the convection cells larger than entire star systems dredging material down to the core. We can track the angular momentum of the infalling gas which must be shed for accretion to occur, a process the turbulent envelope facilitates with brutal efficiency. And at the very centre of these computational universes, we see the black hole's event horizon, expanding swallowing mass at a rate that defies belief. In the span of a mere 1 to 2 million years, the typical lifespan calculated for these objects, a humble stellar mass black hole can grow to 50,000, 100,000, or perhaps even more times the mass of the Sun. It has made the leap. It has crossed the vast empty desert of the mass gap, transforming from a stellar remnant into a true intermediate mass black hole. This is the solution. This is the answer to the seed problem. The quasi-star is the missing link, the transitional phase between the death of the first stars and the birth of the first quasars. It is the universe's own black hole nursery, a purpose-built incubator for growing giants. It doesn't just create a slightly bigger black hole, it forges a fully formed monarch in waiting, a gravitational kingpin massive enough to begin shaping the destiny of its host galaxy. Once an object of this magnitude exists, the subsequent stages of its growth, while still impressive, become far more plausible. 100,000 solar mass black hole has a gravitational reach so immense it can begin to pull in entire star clusters to merge with other black holes to anchor the flow of gas that will build the galactic bulge around it. The quasi-star provides the monumental head start needed to explain the billion solar mass behemoths that lit up the cosmos less than 1 billion years after the Big Bang. It's no longer a mystery requiring unknown exotic physics. Instead, it's an elegant if violent consequence of the conditions we know existed at the dawn of time. These weren't isolated freak occurrences. In the dense chaotic cores of the first proto-galaxies, where colossal clouds of pristine gas were collapsing under their own weight, the conditions were ripe for hundreds, perhaps thousands of these incredible objects to form. They were the secret engines of creation working in the shadows of the cosmic dawn. Each quasi-star that lived and died would have seeded its nascent galaxy with a potent gravitational anchor, a seed around which the first stellar empires would be built. They are the hidden architects of the cosmic web, the progenitors of the galactic dynasties we see around us today in the local universe. We are looking at the culmination of a vast theoretical journey, a convergence of astrophysics, general relativity, and computational science, all pointing to a single extraordinary conclusion: that before the first true galaxies could shine, the universe first had to build these dark, shrouded monsters. But this cosmic engine, for all its staggering power and efficiency, is a temporary creation. It cannot run forever. The vast reservoir of its envelope, while monumental, is not infinite. The relentless torrent of matter flowing into the central black hole is steadily consuming the very structure that enables its growth. A day of reckoning must come, a moment when the fuel runs critically low, when the delicate balance between the inward pull of gravity and the outward pressure of trapped light finally catastrophically breaks. The quasi-star, this brilliant solution to one of cosmology's greatest puzzles, carries the seed of its own spectacular demise within it. Its life, though transformative, is destined to be brief, and its death will be an event unlike any other in the history of the universe. And so, the phantom takes shape. It solidifies in our imagination not as a star in any sense we have ever truly known, but as something far more primordial, far more violent. For the briefest of cosmic moments, these celestial titans likely blazed in the darkness of the early universe, their light a furious scream of matter being torn asunder. We have journeyed back to the very edge of time, to an era shrouded in hydrogen fog and nascent gravity, all in pursuit of an answer to a staggering cosmic contradiction. Supermassive black holes grown impossibly large, impossibly fast. The universe, it seemed, had skipped a crucial chapter in its own autobiography. How could these gravitational behemoths, millions or even billions of times the mass of our Sun, already be sitting at the hearts of the first galaxies? There simply was not enough time, not enough material, not enough conventional physics to account for their gargantuan size in such a fleeting, youthful epoch. The standard model of gradual accretion of black holes sipping patiently from the cosmic reservoir simply fell apart when confronted with the evidence staring back at us from the abyss of deep time. The equations demanded a different path, a faster, more ferocious, more direct route to assembling a monster. This is the intellectual void into which the quasi-star was born. It is a concept forged not from direct observation, but from the unyielding logic of cosmic necessity. It stands as one of the most elegant and audacious theoretical solutions in modern astrophysics, a bridge thrown across a chasm of ignorance. It tells us that to build the universe's largest structures, nature may have first had to create its most paradoxical objects. We began with a mystery etched in the light of ancient quasars, a puzzle of impossible growth. We traversed the collapse of colossal primordial clouds, bypassing the birth of normal stars, entirely watching as gravity squeezed these protogalactic cores into a state of unimaginable density. We saw the birth of a central black hole not as the endpoint of a star's life, but as the very engine of a new kind of celestial object. And now we are left to contemplate the sheer, breathtaking strangeness of the result. Imagine it once more a swollen luminous sphere 1,000 times the size of our own solar system, glowing with the light of 1 trillion suns. A star not powered by the gentle fusion in its core, but by the relentless gravitational fury of the black hole festering within it. The outer layers, a vast envelope of hydrogen and helium, are held at bay only by the ferocious torrent of energy blasting outward from the accretion disk, a cosmic standoff between gravity's infinite pull and radiation's overwhelming push. This is the quasi-star. A temporary, magnificent and terrifying balancing act on a cosmic razor's edge. It is the universe's ultimate shortcut, a celestial forge designed for one purpose: to rapidly inflate a seed black hole to intermediate mass, preparing it for its eventual reign as a supermassive galactic monarch. The solution feels complete, it feels right. It resolves the timeline paradox with a brute force efficiency that feels characteristic of the young, untamed cosmos. But in solving one great mystery, the quasi-star presents us with a profound new challenge, forcing us to reconsider the very meaning of the words we use to label the heavens. What then is a star? For all of human history, the answer has been a source of constancy, a point of cosmic certainty. A star is a crucible of fusion. It is a celestial engine that smashes lighter elements together in its core to create heavier ones, releasing a steady, predictable stream of energy in the process. This thermonuclear fire is the defining characteristic, the very heart of stellar identity. Our Sun is a star because it fuses hydrogen into helium. A red giant is a star because it fuses helium into carbon. A white dwarf is the cooling cinder of a star that has exhausted its fusible fuel. This definition has been the bedrock of astrophysics, the first principle upon which we built our understanding of galaxies of chemical enrichment of life itself. The quasi-star demolishes this simple, elegant definition. It wears the mask of a star possessing a photosphere, a temperature, a luminosity that would make it one of the brightest objects in the entire universe. Yet, it is an imposter. Deep within its convective turbulent shroud there is no fusion to be found. Its core is not a furnace of nuclear synthesis, but a vortex of space-time, an engine of pure gravitational potential energy. The light we would see from a quasi-star is not the product of creation but of annihilation. It is the death cry of gas superheated to millions of degrees as it is stretched, shredded, and ultimately devoured by the central singularity. It shines not with the energy of E-MSIS-2, but with the raw kinetic violence of matter, converting its own infall into a blinding torrent of radiation. This object fundamentally blurs the line between stellar and gravitational phenomena. It is a hybrid, a chimera, a transitional state of matter and energy that may have only been possible in the unique cauldron of the cosmic dawn. It forces us to broaden our taxonomy, to create a new category for objects powered not by what they are but by what they consume. It's a profound shift in perspective. We are accustomed to thinking of black holes as the end state, the dark remnants left behind after a star has lived and died. The quasi-star flips this narrative on its head. Here the black hole is the beginning. It is the power source, the engine, the vibrant heart of the system, while the vast stellar-like envelope is merely a temporary fuel tank, a transient atmosphere waiting to be consumed. This recontextualization is crucial. It suggests that in the early universe the relationship between stars and black holes was far more intimate, more blurred, more codependent than it is today. They were not two separate populations of objects but participants in a fluid dynamic dance of creation and consumption. The existence of quasi-stars, even as a fleeting phase, illuminates a universe far more versatile and inventive than we might have imagined. It tells us that nature, when faced with the problem of rapid growth, will exploit the most extreme physics available, hijacking the power of a singularity to mimic the light of a star, all in service of building the cosmic scaffolding we see around us today. Our neat and tidy definitions, forged from observing our local mature universe, may be completely inadequate to describe the chaotic experimental laboratory of the past. The quasi-star is a humbling reminder that the cosmos is not obligated to conform to our classifications. To accept the quasi-star is to accept a vision of the early universe that is almost terrifyingly extreme. The period following the Dark Ages, the epoch of reionization, is often depicted as a gentle awakening, a time when the soft pinprick lights of the first small pristine stars began to timidly poke holes in the shrouding darkness. But the quasi-star hypothesis paints a dramatically different mural. It suggests this era was not a quiet dawn, but a violent, concussive inferno populated by celestial objects of incomprehensible scale and power. These were not mere stars. They were cosmic lighthouses, each one outshining entire galaxies. Their luminosity, powered by the accretion of matter at rates we can barely conceive of, would have been staggering. A single quasi-star could have single-handedly rionized vast swathes of the surrounding intergalactic medium, its ultraviolet radiation acting like a celestial blowtorch, stripping electrons from the neutral hydrogen gas and rendering the cosmos transparent. Imagine the impact of such an object on its local environment. The formation of normal, smaller stars, the population 3 stars we have long searched for, would have been profoundly affected. In the immediate vicinity of a quasi-star, the intense radiation pressure would have blasted away the delicate clouds of gas needed to form new stars, effectively sterilizing the region and stifling galactic growth. Further out, its powerful winds and outflows jets of matter accelerated to near light speed from the poles of the accreting black hole would have slammed into the surrounding cosmic web. This process would have injected heavy elements forged in the accretion disk's inferno into pristine gas clouds far away. This is a critical piece of the puzzle. The very first stars are thought to have been composed of only hydrogen and helium. But we find traces of heavier elements, what astronomers call metals, in even the most ancient stars we observe today. Quasi-stars provide a powerful centralized mechanism for this early chemical enrichment. They were not just gravitational anchors, They were galactic-scale chemical refineries processing primordial gas and spewing out the raw materials needed for the next generation of stars and eventually for planets and for us. Their brief cataclysmic lives would have fundamentally reshaped the destiny of their host galaxies. By growing the central black hole so quickly, they established the gravitational anchor that would later shepherd the orbits of billions of stars. By clearing out the central regions of gas, they may have set the stage for the later formation of a stable galactic bulge. The quasi-star phase, lasting perhaps only a few million years, was a short but pivotal chapter. It was the universe's adolescence, a period of dramatic explosive growth spurts, awkward transitions, and extreme behaviour that laid the foundation for the more sedate and structured adult cosmos we inhabit. To look back and search for quasi-stars is to search for the fingerprints of the architects who drafted the blueprints of the modern galaxies. They are the missing link, the ghost in the cosmic machine that connects the smooth, simple universe of the cosmic microwave background to the complex, structured and black hole-dominated universe of today. Without them, or something very much like them, our story of cosmic evolution has a gaping hole in its most crucial formative chapter. The universe we see simply should not exist so soon. These objects, these black hole-hearted imposters, make it possible. But for all its theoretical elegance and explanatory power, the quasi-star remains a ghost. We have no direct photograph, no confirmed spectrum, no single piece of smoking gun evidence that says, here this was once a quasi-star. The immense distances and the shrouding effects of cosmic time have hidden them from our view. They lived and died over 13 billion years ago, their light stretched and dimmed on its long journey to our telescopes. So how do we hunt for a phantom? How do we find proof of an object that has been extinct for almost the entire history of the universe? The search requires a new kind of cosmic archaeology, and its primary tool is the most powerful time machine ever built, the James Webb Space Telescope. Webb's unparalleled infrared sensitivity gives us the ability to peer deeper into the cosmic dawn than ever before to capture the faint red-shifted light from the universe's first luminous objects. While directly imaging a quasi-star in its prime is extraordinarily unlikely, due to their rarity and short lifespans, Webb can hunt for their crucial legacies. The primary target is their descendants' intermediate mass black holes. The quasi-star model predicts the formation of black holes with masses between 1,000 and 10,000 times that of the Sun. Finding a population of these middleweight black holes lurking in the centres of small ancient dwarf galaxies would be a profound discovery. These galaxies are like cosmic fossils, relatively unchanged since the early universe. If they host black holes that are far too massive for the galaxy's size, it would be a strong indicator that the black hole formed first, via a direct collapse quasi-star-like mechanism, before the galaxy had time to grow around it. Webb can detect these black holes by looking for their gravitational influence on the stars orbiting them, or by spotting the faint glow of accreting gas, a mini quasar at the galactic core. Furthermore, Webb is a master of cosmic chemistry. It can perform detailed spectroscopy on the most ancient stars we can find, dissecting their light, to reveal their exact chemical composition. If a star was formed from gas that had been polluted by the outflow of a quasi-star, it might bear a unique chemical signature. This signature would be distinct from that of a conventional supernova, perhaps showing unusual ratios of certain heavy elements forged in the extreme environment of a black hole's accretion disk. Finding a star with this specific chemical fingerprint would be like finding a fossilized feather. It wouldn't be the dinosaur itself, but it would be irrefutable proof that such a creature once existed. The search extends beyond Webb. The next generation of gravitational wave observatories, like the planned Laser Interferometer Space Antenna LISA, could open an entirely new window onto this hidden epoch. LISA will be sensitive to the low-frequency gravitational waves produced by the mergers of massive black holes. If the universe was once filled with intermediate mass black holes, the remnants of quasi-stars, then we should expect to see them merging with each other in the early cosmos. Detecting the specific gravitational wave signature, the chirp of two 10,000 solar mass black holes spiraling into one another 13 billion years ago would be an unambiguous echo of the quasi-star era. It would be the sound of the universe building its giants. This multi-pronged observational campaign is not just about confirming a single theory. It is about illuminating a completely dark chapter of cosmic history. We are no longer just passive observers of the universe. We are becoming active detectives, piecing together clues from scattered photons, stellar chemistry, and ripples in space-time itself. The ghost may be elusive, but we are building the tools to finally see it. The hunt is on, and the data is at this very moment streaming back to Earth, holding the potential to transform a beautiful theory into a confirmed reality. Our journey in the end brings us back to that fundamental relationship, the intricate dance between galaxies and the monsters at their hearts. The quasi-star hypothesis is more than just a clever solution to a timing problem. It is a profound statement about co-evolution. It suggests that in the very beginning the galaxy did not build the black hole. The black hole in its guise as a quasi-star helped build the galaxy. This idea inverts the traditional narrative and places the black hole not as a passive consequence of galactic formation, but as an active foundational architect. This is the grand synthesis from the primordial quantum fluctuations that seeded the first density peaks, to the collapse of immense gas clouds, to the birth of a temporary impossible star powered by a black hole. This process didn't just create a seed for a future supermassive black hole, it simultaneously regulated the environment, enriched the cosmos with new elements, and dictated the initial structure of the galaxy that would grow around it. The legacy of these fleeting titans is written across the entire sky. It is encoded in the distribution of galaxies, in the mass of their central black holes, in the chemical makeup of their oldest stars. Every spiral arm we see, every galactic bulge, every intricate structure in the modern universe may bear the faint ancestral imprint of a quasi-star that blazed and died more than 13 billion years ago. We stand on the precipice of a new understanding, peering through the telescopic lens of Webb into the very crucible of creation. We are searching for the ghosts of these first cosmic monsters, knowing that finding them will not only solve the paradox of their impossible descendants, but will also reveal the deepest secrets of our own cosmic origins. The story of the universe is a story of transformation of matter and energy, finding ever more complex and beautiful ways to organize themselves. The quasi-star represents perhaps the most extreme transformation of all, a star powered not by its own life, but by its own inescapable death. It is a testament to the universe's boundless, violent, and magnificent creativity, a reminder that in the deepest darkness of the past, there burned the brightest and strangest of all possible lights. And our quest to understand them, to chase their echoes across cosmic time, is simply the next chapter in our own attempt to read that epic story.